There we go. All right. So today we are on 5.6 notes. This is going to serve as our video reference here. I'll put it up for you to watch if you need it again. Student blank notes here. You can write it on a separate sheet of paper. You can print it whatever you want. This is, again, for those who are not in class right now and didn't hear us talking about this. These are all of the notes. I think on page 15 starts the Fleury notes, or 5.6 notes. If you just go to page 15 here, that will start it, and it goes from page 15 to page 17. And on page 17, that's it. So we are going to go over these algorithms today, and I'm just gonna have my teacher notes here for you to look at, okay? Now, if you remember back in 5.5, we talked about Euler's theorems, and that was where we had those shortcuts that we learned about. If you haven't done that yet, you may want to go back and look over 5.5. It is very helpful for you to have those shortcuts to figure out what a Euler circuit is and a Euler path. And because we know that Fleury's algorithms actually talk about, as you can see, does a Euler or an Euler circuit or Euler path exist in each graph, okay? So we're going to look at these two, the circuit being you start at a point, go around, hit everything, and then end back on that point, and the path being you start at a point, you can hit everything one time, but end somewhere other than the point you began. Now, we're going to do this by identifying the start and end number of the edges in order. So if we started here, which again up here, it just find one, you can start wherever. So if I start here, I'm going to number where I go and where I end. So that's really all I'm doing. And we've done this already, but this one says that I started that way. It's kind of like a maze, right? So I started here, there's 1, there's 2, 3, 4, 5, 6, 7, but then I went down 8, up 9, 10, 11, 12, 13, 14. That is a Euler circuit, and you're going to order or number the edges that you take. So you can start anywhere on a Euler circuit and end up at the same place. So even though I did it this way, if you're going to do a practice problem in the future and you see an answer key, you might not want to start where I started. Any point that I chose, and you can count the vertices, right? There are 9 vertices. There are going to be so many different paths that you can take. So if you take mine, you know, I get a little curious as to, did you actually do that on your own? So a Euler circuit, you can start anywhere. If we start here on this one, right, and I started here, so you can see my starting point. There's 1, 2, 3, back up 4, back down 5, across 6, down 7, diagonally up 8, diagonally up 9, down 10, and across 11. I couldn't start anywhere here. This is actually a Euler path, right? You started here and ended here, so it's a Euler path. But what you must do, and something we talked back in 5.5, on a Euler path, you need to start where the vertex or vertice has an odd degree. So you can notice right here, I started at this vertice and I've got 1, 2, 3, an odd degree. I could have started over here at this vertice, I've got 1, 2, 3, an odd degree. You can go in whichever direction you choose at that point, but you must start and end at those odd degrees. So there's still multiple ways you could have done this. Not one, there's multiple, but here again, you must start for a Euler path at an odd place. So what does this do? What does the Euler theorems tell us about the graphs? And let me zoom in. It might be hard for you to see there. Remember, you can, if you're in the Google Meet, pin this, and it will be a little bit bigger for you to see if you've not already done that. So what do Euler theorems tell us about a graph? The Euler theorems that we learned back in 5.5 do identify the existence of a Euler circuit or a Euler path before we do anything. It's no guess and check game. It's a shortcut, right? It's going to identify whether or not it's a Euler circuit or a Euler path. The Euler theorems actually do not find a specific one, though. So by looking at it, what we know from the Euler circuit, what we know from the Euler path is that, okay, it exists, right? We know there is one there. But what it does not do is it doesn't tell us right, where they go. So we know it's there, we know it exists, but the Euler theorems don't tell me where they are. So how have we been finding these Euler paths and circuits? We've been doing that open and closed unicursorial tracings. If you remember that from like 5.1 beginnings, and then even after that, talking about the unicursorial tracings. Well, we've done trial and error and the guess and check game, right? We start here, we keep going around. Oh, that doesn't work in a race, right? It's time consuming, it's complicated, you get frustrated, you say, Mr. Hall, you give me too much work, and you type it up in an email and you hit send, right? But, you know, can we shorten that? Maybe. Let's see if Fleury's algorithm actually has any help for us here. So this is what we call a directive-driven Fleury's algorithm. The idea is don't burn your bridges behind you. What does that mean, right? Don't burn your bridges behind you. Bridges, graph theory bridges, not in the real world, right? We're talking about if there is a spot where you can go across, right? And if you erase that edge, and that's the only way you can get to the other side, that's a bridge, right? It's kind of got a degree of one, two vertices, right, that only have one thing in between them. That's a bridge. So the idea here is don't burn the bridges in the graph theory. So fact number one, an edge can only be traveled once in a Euler path or circuit. So as you trace the edges of a graph, you are limiting the parts of the graph that you travel on. As you start to trace, now you've kind of said, well, I can't go that way anymore. You know this, right? You might not have put it in writing, but you know that. In fact, number two is that in the remaining graph that you have, certain edges that you choose might get you stuck and prevent you from going in any other direction. So without retracing them, those would be what we consider bridges. We don't want to burn those. Okay, the concept of a bridge occurs in the yet to be traveled portion of a graph, the remaining graph, right? So here are our steps that this guy, Fleury's, has decided to use. A nice little graphic table here. You know I love my tables. So we've got 3 steps, and one is for the Euler circuit, one's for the Euler path. Let's focus right now on the circuit. So step number 1, the existence. Determine if it is a Euler circuit. So that's the whole thing that we typed in and wrote before. The graph is connected and has no odd vertices. So that's when everything has even vertices, even degrees on all the vertices. Does it exist? From Euler's theorem. Okay, it exists. Step number 2, starting vertex. According to Fleury, what are we going to do? We're going to choose any vertex unless given a specific starting point. If it's just open to interpretation, you choose where you go. For a Euler circuit, any vertex can be used to start and end on because it's a circuit, unless they tell us otherwise. So the intermediate steps, what do I do after I started and before I finish, right? So what you want to do is label the edges that you've already traveled. This is good practice. It can be a highlight, but you probably want to put a 1 there so you know when you traveled across it, right? A 2, a 3, like we did at the beginning of this. So label the edges you have already traveled by numbering them in order. In the remaining graph, first always choose an unused, untraced edge that is not a bridge at your current vertex, because as soon as you use that, now you can't go back. Finally, only choose a bridge if it is the only option at your current vertex. So basically, it's like this. If there's a bridge, choose it last. If there's not a bridge, choose that one before you choose the bridge. That's his idea, right? But the same is applied in the Euler path. Notice that these two overlap, kind of like a Venn diagram. This last intermediate step is applied in both of them. It's applied in the Euler circuit and it's applied in the Euler path. The only difference is that in the Euler path, what we talked about a moment ago is that you must choose between the odd vertices. And you should only have 2, right? From the theorem that we learned last week, right? Last Monday, so a week ago, try not to forget all that, is a Euler path has exactly 2 odd vertices. So choose one of them, start there, make sure that you don't use a bridge unless it's my only option left. Okay. So examples of Fleury's algorithm in place. And an algorithm is just a stepping process, right? That's all an algorithm is. It's not a theorem. It's just like, we're going to do it in this particular order. So, and I've got the answers here, but we're going to determine if each graph has a Euler path or a Euler circuit or none. If it is one of them, find it in the graph by numbering the edges that we use. In a Euler circuit, pick vertex A for your start. In the Euler path, just pick the odd one. So wherever vertex A is, if it's a circuit, start there. And if it's a path, just find one of the vertices that's odd and start there. So for graph number 1, right, this is a Euler circuit. Why? If I go and count the vertices degree for each one of these, A has a vertice or a degree of 2. I guess I am going to draw here. This has a degree of 2. B has a degree of 4. C again at 2. D over here has 4. E, 1, 2, 3, 4. G, 2. And F, 2. So all of the degrees there are even, therefore it can be a Euler circuit. So at this point, what you would do is find the Euler circuit starting at point A. And we cannot cross a bridge. All right, so I'm going to change the color here so you know where I start and where I end. So if I start at A, I can go from A to B. So that's 1. Right? That's not a bridge. Why is it not a bridge? Well, because I can still come back this way. From B to C, that can be 2. Not a bridge. From C to E, I can do that one. We'll call that one 3. It's my only option left. Now I can't go backwards, right? Now from E, I could go up to B. So why don't we do that? Why don't we call that 4? From B, I'm going to go down here to D, and I'm going to call that 5. Now, from here, I cannot go back to A. We would call that a bridge. Why? Because there's no other way that I can get from D to A because I can't go anywhere else. So we're not going to go that direction, right? We can go down to F or across to E. So let's go across to E. Let's call that 6. E down to G, we'll call that 7. G back to F, we'll call that 8. And these are the ways that we must go. F back up to D, we'll call that 9. And then D up to A, because that's the only option I have left. And there's 10. There's my circuit. Why is it a circuit? We started at A. We ended at A. Okay? For graph number 2, what we have here is a Euler path. Why is it a Euler path? Because if you go through each one, and I'll go back to the original colors, I think, we'll see. A has a degree of 2. G has a degree of 2. D has a degree of 3. There's a reason it's highlighted. E has a degree of 4. F, 2. H, 2. B has a degree of 2. And then C actually has a degree of 1. Now, this is a prime example of a bridge. In a Euler path, what Fleury's said, start at one of the odd ones and don't burn the bridge unless you have no other option. We know it's a path, so it's got to start and end at different spots, right? So what we're going to do is choose either D or C. I'm actually going to go to C for a second because I want to focus on this idea of burn a bridge only if you have no other option. C has a bridge between B and C. There's no other way to get back to C, right? So I have to burn this bridge because that's the only way that I can go. So I burned it. The idea is not to unless I can't help it. So I burn that bridge, I'm done. Now I'm going to go from B to E. That's 2. We can still do the path even though we burned the bridge. From E, I could go back over here to D. I could go over here to F. It doesn't really matter. Since we're going to start and end at different spots, I'm going to go back over here from E to F and do that 3. You might have gone the other way. F to H, we'll call that 4. H to E, we'll call that 5. There's a bridge between E to D, right? From E to D. If I would have went back this way, right, from before. That's a bridge. If I would have went from E to D, I would have burned that bridge and never been able to get back to the other side and finish off this Euler path. That's why you go back over here or you go down and up. Okay, you had two options to go, but you couldn't go back towards D. Now, since this is the only option I have, I'm going to need to burn this bridge. And now I can decide where to go from there. So from D to G, maybe I decided to go down. There's 7, there's 8, and then back to D, 9. So we started at an odd and we ended at an odd. But I had to burn the bridge in the process so that I didn't leave a section of this graph which is unobtainable. So I hope that makes sense in Fleury's algorithm. So instead of doing a guess and check and just blindly going through, now we have this idea that helps me to find where I need to actually take those numbers and trace in our graph theory. Okay, I'm going to need to clear this. This is being recorded, so you can always go back. I believe once I get done with 3, 4, 5, and 6, I will let you do the last ones. But I do want you to see this again. And I'm just going to start, and instead of numbering them all, right, when I find a circuit or when I find a path, we'll start where the instructions told us to start. So in graph number 3, I'm telling you right now that this is a Euler circuit. How do I know? All of them have an even degree. You can go back and fact check me if you want. In fact, you should, but all of them have a even degree. So now in the instructions, it says if it's a circuit, you start at A. So I start here at A, right? And I cannot burn a bridge unless it's my only option. So there is actually no bridges here to begin with. So I can go in any direction I want, right? I could still get to E if I burn this, right? I can still get back up. I can still get to C. If I burn that, I can still go back and around. I can still get back and around. So only a bridge if you can't go back to where you were. That's what a bridge is. So why don't we, trace this in numerical order as well. So why don't we call that 1, or alphabetical order. Now B can't go back over here to C, so I'm going to come down. So that's 2 because I can't go any other way. Now I can't go back to B. That's fine. Now what I could do is I can go down here to F, or I can go back up to A. Doesn't matter. Why don't we come down here to F? So I can show you there's multiple ways. You might have thought maybe I went to C, maybe I go back to A. I'm just going to go down. So from here, from F, I'm going to go from F, maybe I only have one other option, and that's back up here to C. So I have to use that now. From C, I could go down. Why don't we just keep going around the perimeter? So 5. Use this edge right here, 6. It's my only other option. I'm back at A. Now I've got 2 options. Go down to C, across and up, or down, across, and up. Doesn't matter which way you go. I'm just going to go here 7, here 8, and then back up 9. Looked complicated, but it's actually less edges than the one we've done in the past. There you go. There's a Euler circuit. Hopefully that makes sense. But we have to start and end at A because that's what the instructions told us to do. Let's look at graph number 4. Another Euler circuit here. They all have even degrees. A has a degree of 4. Remember a double edge, 1, 2. Remember loops count for 2 as well. So 1, 2, 3, 4. All of them are a degree that is even, so we have to start at A. Instead of going from A to B, I'm actually going to do something a little off the cuff here. I'm going to go down here to D. I'm going to go A to D. I'm going to go back up to A. So I'm going to call that 2. So now I've got that middle taken care of. Now I can go down here to C, or I can go back over here to B. I'm going to go down to C. I'm going to go opposite of what you think, right? And maybe that's what you wanted to do anyway. I don't know. I don't know who you are. Now I'm going to go on this outside one, call that 4. Maybe go back up to C. We'll call that 5. Go back across because now that's my only option. We'll call that 6. I can go down. Why don't we go down? Make that, actually, no, I'm not going to go, no, I'm not going to go down. I'm going to go down over here to G. I'm going to call that 7. Go back over here. Now I'll call that 8. Back up, we'll call it 9. And now I have one path. I've got to go back over here to B. We'll call that 10. It's a circuit, so we need to stop back at A. B down to G, either way you want. We'll call that 11. And then this one, 12. And then back to A, 13. Hopefully you're starting to get the idea of not burning a bridge and you're visualizing where you're going to go next. But also, you don't have to ask, which way do I go? Right? You don't have to ask us every time, which way do we go? Because there is some method to this madness. Okay, I'm going to do 5 and 6, and then I will let you, well, I'll do 5. I'll do one of the other ones, and I'll let you practice from there. So why don't we move down here to number 5. Trash. Grab and move down. Let's just do number 5 together. Remember, in a Euler path, you must start at an odd degree. This is a Euler path. I'm telling you it's a Euler path. Believe me. The highlighted ones are the odd degrees. E is 1, 2, 3, 4, 5, and so is H. 1, 2, 3, 4, 5. I don't care where you start, just don't burn a bridge. So E, why don't we start by going in? There's 1. Where you start, you must then end back at the other degree or other odd vertice. So whatever you want to do, right? 1 down here to 2, maybe across 3, up 4, I don't know, back down 5. I burned that bridge, even though it's not technically a bridge, I can still kind of get and maneuver around, but it's going to be like going out and around to get there. So I'm at J. I can't go back up. I can't go any other way. So I'm going to have to go this way here. 6. I don't know. Maybe go back up. 7. Back across. 8. Up. 9. Down 10. Back up 11. And back over here to be 12. So you can see kind of where I'm dealing with one half before I go to the other half. Do you always have to do that? No, there's other ways, but then again, that's like the guess and check game. So there's 13. We did not use this one here, so we can go down 14. If I do that, now I need to go across because I can't go down. We'll call that 15. I'm going to go down here, 16. I could have gone up, over, and down. And now I got to go over here. So that's 17. This will be 18. Okay, so that was 15. So I can go up, across, and down. So this will be 19, 20, and then back down 21. And so you've seen how all of that got dealt with there. All you need to do is number those off. And the biggest thing is don't burn a bridge unless you absolutely have no other choice. And you're not always going to run into bridges. But if you do run into a bridge, try your best not to burn it. Because if you do, you're just going to have to start over and do the guess and check game. I'm going to stop the recording now. And I want you to work on the rest of these kind of as the are you ready for more type deal here. Okay?